If I asked you to picture a solar panel anywhere, you'd probably picture it on someone's house roof or in some sort of open grassland. And the problem with these solar panels is that they're only 15 to 22% efficient, which is why researchers in the space have been trying to get some better materials, more efficient ones that can hopefully increase this efficiency to get more output from the sun that goes into the energy storage system. And people have been coming up with new designs like perovskite cells, which are now becoming more and more ubiquitous. A simpler solution that my team and I thought of through a hackathon a couple months ago was rotating solar panels. The sun isn't in direct contact with the solar panel throughout the entire day because it's stationary. So let's say the sun is over here in the morning and the solar panel is like this. The sun gets the most amount of direct contact with the solar panel when the solar panel is in a perpendicular position to the sun. So if it's like this and the solar panel is like this in a perpendicular situation, then there's the most amount of contact possible. But because the sun moves in this direction, then there is no sun being put on to the solar panel, which means that there's not going to be much output throughout the rest of the day. So from that idea, a couple months later from the hackathon, I took the opportunity to build out a dual axis solar panel, which basically just does that, where it rotates to get the most amount of sunlight possible so that it can take as much output to the energy storage system later on. And in this video, I'll be explaining the materials I use for this, including Arduino, and how I got about building this. Okay, so to understand how this would work, you need to understand the mechanism behind most of the main components. So obviously you have the solar panel, but I'm not actually doing anything with the solar panel because in the short term, to calculate at an instant where the light is being shined down, you need to use LDRs, which are light dependent resistors. And these basically just find sensor values of where most of the light is being shined upon with 4 different LDRs on each side of the rectangular solar panel. So if I turn this around right here, you can see that there is an LDR over here. This represents the north side. There's an LDR over here, which represents the south side. There's an LDR over here that represents the west side. And this LDR represents the east side. So based on the values in each LDR, which basically measure how much light is being shined upon on that specific LDR. If it's very high, then you know that, let's say you shine the light here, it's going to be shined on the north side. And based on that, you do a certain command based on if statements. And you keep doing these if statements until the LDR values are balanced. By balanced, what I mean is to find if it's actually balanced, you need to take the differences of all the 4 LDRs and make sure they're within a certain range. Because obviously all LDRs are different. They've been on this earth manufactured for different times. So some of them might be older than others, and some might not be as well functioning as others might be. So there's a range of 100. So if the values are within a range of 100 of each other, then it means they're balanced. So that's how you would know when to stop. If it's balanced, then you stop. And if it's not balanced, then you try to find where most of the light is being shined upon. And based on that, you do certain if statements. Okay, so for the next part, you need to understand the DC motors. And I'm using 2 DC motors. The first one is placed over here, and the second one is placed over here. The bottom DC motor is controlling the way the solar panel is moving. So like this and like this. That's the bottom DC motor. And you have a rod that's connecting to this platform that is connected to the other DC motor, which controls the angle of the solar panel. And you can see that there is a gear over here. So when you have the DC motor that is moving the rod, the gear just adds more power so that it can move this even more heavy object, because the rod itself can't just control a complete big solar panel. So you would have a gear that controls the angle that the solar panel is moving at. And so that's basically what the 2 DC motors do. And you have obviously a bunch of wires being connected with each other. And then from there, what you also have is to connect the 2 DC motors, you need an H bridge to specify the amount that the solar panel moves whenever the light is being shined on one of the LDRs. So I have an H bridge as well. And then the rest are like normal Arduino components. And then under this, where the LDRs, obviously they're hidden, but I don't know if you can see that well, but this cardboard is taped to the bottom of the solar panel. And the bottom of the solar panel, not only does it have the LDR connections, it has resistors and it has pins that connect to the analog pins for the LDRs and the digital pins and the ground and the 5-volt pins, so that you have basically a functioning LDR. And the way I did this is by soldering. So I use soldering equipment to soldering iron, even put in my hands, but that's beside the point. And I basically soldered it together, put it under the solar panel, taped it on the cardboard, and then you have this solar panel project. Okay, so to test this out, I'll be using my phone flashlight, and I'll be pointing it in different directions of different LDRs to see how it would move if I pointed it on the north side, the south side, the east side, and the west side. So let's start with the north side, which means it should move this way. Okay, and then let's do the south side. Okay, and then let's do the west side. Okay, cool. I'm gonna put it back a bit to the north side, so, okay. And then I'll do the east side. Okay. Well, that's what it thinks the east side is balanced with. The one limitation I would say, and this is because this is a smaller project, not completely scalable, and this is, again, a limitation, is that, not sure if you can see, but these wires are kind of short. And so I have a bunch of wires connected to a bunch of wires, and that's how I made it able to move a certain amount of degrees. But overall, if you wanted to rotate it again and again around, obviously these wires would come out unless you had wires that were infinitely long. So that's a limitation to have, but because this is more of just a prototype and not like obviously really scalable to the point that you can implement it at a solar farm, because obviously the solar panel is pretty small, the wires is a limitation, the foundation is also a different thing, but it's a pretty good prototype in itself, and I hope you enjoyed.